All right, guys, we are now moving on to trigonometry. Now, this first unit that we're going to do, the first lesson we're going to do is probably going to be a little bit of a review, hopefully a little bit of review from geometry, maybe some classes before geometry and things like that. But trigonometry starts, the basics of trig is on the study of right triangles. Now, trigonometry itself is a study of triangles and angles, more so angles, but the basis of trig is based off of right triangles. So that's where everything starts from. That's where your trig functions come from, the trig ratios when we get into that. So this is a great starting point. So the most basic thing when you think of a right triangle, hopefully, is going to be this Pythagorean theorem. This is something that you've seen before. So I'm going to start with that real quick. So when you have a right triangle, and again, obviously, everything we're doing today is going to be with right triangles, but Pythagorean theorem especially, there are three sides that you get with that triangle, and hopefully you've seen these before. So those three sides are going to be called A, B, and C. So those are the three sides that you see in a triangle. Now, the only thing that really matters here, C is your hypotenuse, A and B represent the legs. So we have a leg here, and we have a leg here. And then obviously this is the hypotenuse. And the Pythagorean theorem, which again I hope you've seen before, is going to be a squared plus b squared equals c squared. So this formula is obviously used to find side lengths of a triangle. Again, a real quick example as we go through this. I'm not going to spend a long time here, but this is more of just a refresher. So real quick example. All right, so quick example here, just finding the side of a triangle, the side length of a triangle. If we have two sides using the Pythagorean theorem, we should be able to find that third side relatively quickly. Now I'm leaving out some basic ones. This one is example 2 in your notes. But this one, if you see it here, all we're going to do, and it doesn't matter which side you start with, I can call this A if I want. Therefore, I'll call that B, and then I'll call this C. Remember, these two don't matter. You can call them, this 22 you can call A, and the X you can call B. Again, it doesn't matter. The C has to be the hypotenuse, though. So here we're going to just go A squared. Actually, I'm going to call that X squared, so don't mind my messy board here. This is going to be X squared plus B squared, which is 22 squared, equals C squared, which is 24 squared. So in these, obviously, we may use a calculator if we have to multiply that out. So 24 squared and 22 squared, we're going to get X squared plus 484 equals 24 squared, which is 576. So to solve this for X, we're going to subtract 484 from both sides. So those cancel. So this is 576 minus 484. So we get 92. And then we just need to simplify here. So in order to simplify, a little bit of work with radicals, and you're going to see us doing a lot of work with radicals in this unit, because again, you're dealing with triangles, these are probably going to pop up. But what we want to do here is we want to look at this 92, because I want to simplify it now. And obviously, the square root of x squared is x, but the square root of 92, we want to see if they have any perfect squares. So if I pull out a 4, so I'm going 92 divided by 4, I'm going to get the square root of 4 times 23. So we are going to need to simplify these as we go through. We don't just write the decimal. I'm going to want a simplified radical on these. So in this case, the square root of 4 is equal to 2. So as I write my final answer, I'm going to get 2 square roots of 23. And that is going to be your missing side in terms of a radical. So that is going to represent, again, your Pythagorean theorem. Again, I can do a lot more examples of that, but we've seen it before. So this is just more of a quick reminder of what that is. And then we're going to move on to what we did in geometry, which was special right triangles. So in your notes, you'll see two special right triangles that are drawn. So I'm going to go ahead and put those up here now, starting with a 45, 45, 90 triangle. So with a 45, 45, 90, these are, this is what's also called an isosceles right triangle. Now, before I really get into this too much, as I said, right triangles are the foundation of trigonometry. Now, the two triangles that really get used, I would say about 90%, probably more than that, in trig, are these two triangles I'm about to put up. So again, think of the entire subject of trigonometry. In one way, shape, or form, about 90% of it can be related back to the 45, 45, 90 and the 30, 60, 90 triangles. They, again, are the foundation of trig. So knowing them and these ratios, I can't even explain enough how important this is to know. Okay, this is, again, a foundational concept. So with a 45, 45, 90 triangle, again, these angles are both 45 degrees. So the sides, these two sides are equal in length. So we'll call them, and I won't use x, let's use A and A. I don't like to use x because usually in a problem we do, the variable's called x, and it might get confusing because that variable x might not mean this x. So we're going to use A, and if these both sides are A, again, I can prove this if I did Pythagorean theorem. What you would get after you do Pythagorean theorem, you apply your radicals to help you simplify, you're going to get a square root of 2 for your hypotenuse. You must know this. This is, again, extremely important. And there's a second triangle we need to know, and that's your 30, 60, 90 triangle. So I'm going to put that right here as well. So this triangle, again, is not isosceles, which means the two legs are of different lengths. So in this one, the way I drew it, the smaller angle right here is 30 degrees. Notice that opens up to your smaller side. The larger angle, which is 60 degrees, opens up to your larger side. Now the smaller side in a 30, 60, 90 is going to be equal to A. Now if that's and that's just a variable, but it's a number. Now if that number is A, then the larger leg, the leg across from the 60-degree angle, is A square roots of 3. And then if you have those two sides, your third side is going to be equal to 2A. So again, your shorter leg is A, your longer leg is A radical 3, and your hypotenuse is 2A. Notice I did not say the bottom is A. The side is A radical 3, because this triangle can be turned a couple different ways. I can draw it like this with the 30-degree angle is on the side. So again, we don't look at it as bottom left-hand side and right-hand side. We look at it as short leg, long leg, hypotenuse. So once you know these, and again, you have to know them, then we can move on to solving them. And this is just getting us started. I haven't really even done true trigonometry yet. This is preliminary stuff. We can't do the trig if you don't know this. So now that we hopefully are going to start to learn it, I can talk about applying this concept. So a couple examples I'm going to do. I'm going to start with number 3. So with number 3, we have, let me draw this real quick. Okay, so here's number 3, and as you can see, it's a 45, 45, 90 triangle. So since we have a 45, 45, 90, we are here. Now again, you need to stop having to look at this. As you learn it, as you remember it, because you did it in geometry, then you can look back for now, but you're going to have to learn it. Now, the side that I'm given, if you look, is going to be one of these legs. So I am given A. So in this case, I like to always remind myself what A equals. So in this case, A is 10. So now that I know that A is 10, X, which is also equal to A, because both of these are equal to A, that's also 10. So again, I know that X equals 10. So I can come up here, I can plug it in, I have it. Lastly, we're looking at the hypotenuse. Now you look over here, the hypotenuse is equal to A radical 2. Well, we know that A is 10, so I know that Y is equal to A square root of 2, so that's equal to 10 square root of 2. So we have Y. Now in a problem like this, you're just substituting. And that's, again, that's all I did. I substituted. Now you don't always just substitute. But when you get that opportunity, take advantage of it, substitute, and you're good to go. Now the next one I want to do is going to be number 6. Okay, so for number 6, now notice you'll see that we have a 30, 60, 90 triangle. Now it only is given the 30-degree angle, and you can see that that's a right angle, and again this is going to be 60 degrees. So once you have those sides, or those angles, and you got your side, you're ready to solve. Now realize what you're given. Now in this case I'm given 8. Now 8 in this case is my hypotenuse. Now the hypotenuse is equal to 2a, so that's going to equal 2a. Therefore a is equal to 4, because as you can see 2 times 4 is 8. This is crucial because once you have a, you can just substitute everything back in. So now that I have a, I can now find x. So x is equal, this is my short leg, see it's across from the 30-degree angle. 30-degree angle is my a, so x is equal to a, which is equal to 4. So again, we have my first side, I'll just circle it here so we have it, it's easier. So that's my x value. My y value, that's equal to a radical 3. Well, a radical 3, again, we know that a is 4, so we're just going to plug in a 4 here, and we get 4 radical 3. Again, not too much to worry about on that. So that is my a, my x, and my y value. And again, we had to do a little bit of solving, nothing crazy, and we were able to solve that one. So that's number 6 using a 30, 60, 90. Now they do get a little bit harder from here. Nothing crazy, but they get a little harder. So here we go, number 7. Okay, so for this one, notice again we're given this side. This is my long leg. We are dealing with the 30, 60, 90. Your long leg is equal to a radical 3. So this is where things get a little bit crazier. So a radical 3, in this case, is equal to 27. So now we're going to have to do a little bit of simplifying, working with radicals. So in this case, I'm going to have to solve this for a, because I need a to find my y. And remember, this is equal to 2a. So I'm going to divide both sides by the square root of 3, which leaves me with this. So once you have that, we need to rationalize our denominator. If you remember how to rationalize the denominator, we multiply the top and the bottom by this radical. This is just a part of the simplification process. So I'm going to multiply the top and bottom by the square root of 3. So I end up with a equals 27 radical 3 divided by radical 3. Those cancel. You can also write as a square root of 9, but it's 3. And this allows us to simplify this fraction. You'll notice that a simplifies, the 27 and the 3 simplifies to 9. So a is equal to 9 square roots of 3. This is super important because now that I know what that is, and again, notice it took a little bit of work here to get there. Unlike the last one, we just divided by 2, we were done. Here we had to divide by a radical 3 and rationalize. So it took a couple more steps. It's the same problem really as number 6 though. Once I get to that point, then what we're able to do is find y and x. Remember y, that's my short leg. My short leg is equal to a. So y is equal to a, which is 9 radical 3. So that's my y value. Remember your x values are hypotenuse, so it's going to always equal, in this case, 2a. So my x value, which is equal to 2 times a, so that's going to be, and I'll put it down here to run out of room. So this is going to be 2 times 9 radical 3. That's going to now equal 18 radical 3. So there's your x value. So again, to get your y value and your x value, you have to figure out what a is first. So that's what I did. I used the number I had, set it up in terms of a, solved if I have to. And then once you have a, you can start substituting, but you got to solve for that first. So that's going to be Pythagorean theorem, and that's going to be special right triangles.